Assalamu alaikum, students. Can you hear me?
Alaikum.
Okay, so last time we started chapter number 7, and in chapter number 7, our main focus was to study the concept of entropy. We introduced the concept of entropy, and we discussed that how we can actually get the values of entropy uh, through the tables, as well as then we discuss about how we can get the change in the entropy through the TDS equations. And then we also discussed about if the process is if it is an approximate analysis, or the constant specific heat values, or the cold air standard assumption, then how we do the uh, how we determine the change in entropy, as well as if it is an isentropic process, then what are the equations to relate the temperature and pressure and the specific volume. Similarly, we discussed that if the process needs exact analysis, or if we need to consider the variable specific heat values, or if nothing is mentioned in the question, then how do we determine the change in the entropy? And if it is an isentropic process, then what are the correlations that we are going to use? So we discussed about this formula sheet, and actually within the formula sheet everything we discussed. So this is for the case of approximate analysis, this is for the case of exact analysis, and these are the change in the entropy values, and this is for isentropic processes. These are the equations for the approximate analysis, and these are the equations for the exact analysis. So these are some of the things that we discussed last time in our class. Then now we are going to study about isentropic efficiency. So before proceeding further, first of all, I need to ask, whatever the things that we covered last time, anybody have anything to ask? Any question regarding that? Please, you can ask. Everything
It's clear, sir. Everything's
is
clear.
clear. Okay. Okay, so let's move forward. Let's talk about the isentropic efficiency of devices. Okay, so first of all, when we say about isentropic efficiency, first of all, entropy is linked with the heat transfer. Okay, so as you know that we have ds is basically del q over t. Okay, so we already say that del q is equals to tds. These are the equations for the case of entropy. So whenever we have a change in entropy corresponding to, there must be some amount of heat transfer. Heat must be going in and out of the system. However, if we say that the process is isentropic means entropy is constant, means ds is 0, means S1 is equals to S2. If this is the case, that ds is 0 and S1 is equals to S2, that means isentropic process. So for an isentropic process, this thing is 0. And this thing is 0, the only possibility that ds is 0 is when del q is 0. And whenever we have a process in which there is no heat transfer to and from the system, that kind of a process is known as adiabatic process. So whenever del q is 0, that means it is adiabatic process. So first of all, the point of understanding is that whenever we say isentropic process, it also means the adiabatic process. So isentropic process is very similar to adiabatic process, or it could be used interchangeably, because the entropy change is associated with the amount of heat transfer by formula. So if there is no heat transfer to and from the system, then the entropy change will be zero. So for an isentropic process, it is also considered as an adiabatic process. So this is one point. Anybody want to ask anything?
नहीं sir, say it. समझ आ
Okay,
गया.
okay. So that's why you're going to see in future that you will have numerical problems where isentropic and adiabatic are used interchangeably. So we are considering isentropic efficiency, but it will be written in the question that, let's say we have a compressor which is adiabatic compressor. So you need to understand that there is a relationship between adiabatic and isentropic. Okay, so anything isentropic must be adiabatic. So this is the relationship. Okay, so let's talk about isentropic efficiency. When we say isentropic means entropy remains same, and the other way round, if we say the definition, it means uh, entropy same means there is no entropy generation, and there is no entropy generation means there is no irreversibility in the system. That means if there is no irreversibility in the system means there are no losses in the system. Now, there are no losses in the system means it's an ideal system. So whenever we talk about isentropic devices, an isentropic process or an isentropic device is a device where there is no losses in the device. Okay, so let's talk about the most common example. Suppose we have a motor. Motor is basically what? Motor is a device which will use electrical energy and converts it into mechanical work output. Now, if the motor has no losses, then what will happen? That the amount of electricity that you are going to provide to the motor, all of that electrical energy will be converted into work output. Okay, this kind of a motor will be the isentropic motor. But in reality, you don't have anything isentropic. In reality, you have losses. In reality, you have irreversibilities. So the motor has a lot of components which are moving against each other, and there is friction between the components. So there will be some wear and tear, and there will be some amount of heat generated. And that heat generated because of the friction will cause the motor to heat up. And when there will be heating up of the motor, so that heat is going to be lost into the environment, that can never be returned back, that can never be reversed back. So this is a kind of a heat loss, this is a kind of an energy loss. So that means where this energy is coming from, this energy lost is actually being coming from the electrical energy provided to the motor. So that means in real life, the motor will not be isentropic. So all of the electrical energy will not be converted into work output, but some of it will always be rejected as heat output going because of the friction within the motor, because of the irreversibilities in the motor. So this is the concept. So anything isentropic means there are no irreversibilities, and whenever you have irreversibilities, so the one of the major irreversibility, one of the main irreversibility is the friction. So it's like saying that you have a device with the friction, and whenever you have friction and there is motion, so the friction motion with the friction causes heat, and this heat is an irreversibility because this heat generation is going to be lost out of the system. Okay, so in reality, if what happens is that when we supply electrical energy, part of it is being converted into work output and another part is being lost. But if it is an isentropic motor, so then there will be no heat loss. So heat loss is associated with the irreversibility. Okay, so when we say that, suppose if I have an isentropic motor, so in case of isentropic motor, it will also be adiabatic. Because it is an isentropic motor, there is no irreversibility, there is no friction. No friction means no heat generation. No heat generation means no heat loss. So there is no heat going in and out of the system if my system is the motor. Okay, so that means that an isentropic motor will be a motor where there will be no heat loss from the motor. Okay. So whenever we don't have isentropic, there will be heat losses. Okay, so that's why isentropic and adiabatic are quite related with each other. So anyways, a lot of discussion over isentropic and adiabatic devices. Anybody have anything to ask? Are you catching up with me?
Yes, sir. Some of that.
Okay. Okay, so let's talk about isentropic efficiency. So isentropic efficiency is basically what? It is the ratio of the two works. Okay, so let's discuss about it in a minute. Let's talk about a turbine. Now, what is a turbine? Turbine is a device we discussed in chapter number 5. It is a device which is used to convert pressure energy into work output. Okay, now if the turbine is adiabatic turbine, means the turbine have no loss of heat energy from it. Okay, then the process through the turbine would be isentropic, and so there are no irreversibility in the turbine, and all of the pressure energy will be converted into the work output. So for an isentropic turbine, all of the pressure energy will be converted into work output. But in reality, what happens is that we have a turbine and which is not isentropic. Okay, so there are irreversibilities in the turbine, there is friction, there is wear and tear within the components of the turbine, and so there will be some heat generation in the process of this in the process through the turbine, and that heat generation is lost from the turbine surface, so the turbine does not remain adiabatic. Okay, so in this case, what happened is that all of the pressure energy will not be converted into work output, but some of it will be converted into work output. The other part of it will be lost as heat. Okay, so our work output will be reduced in case of an actual turbine. Now, how do we define the efficiency? The efficiency of the turbine, we define it as it's in reality when we write the efficiency is output over input, but in this case we cannot define it as output over input. Rather, what the way we define the efficiency of the turbine is the smaller value divided by bigger value. So at the numerator and denominator we both have work. Okay, but one work is actual, other work is the ideal. In case of the turbine, the actual work would be less. Why? Because part of the pressure energy will be converted into heat loss, so the actual work output would be less. So in case of the turbine, the actual work would be less than the ideal work. Ideal work is when there are no losses from the turbine, there is no irreversibility within the turbine, so all of the pressure energy will be converted into work output. So that kind of work produced is considered as an isentropic work output. However, the actual work output is the one where we have losses in the system. So in any case, for the case of turbine, the actual work output would be less than the isentropic work output. So actual is less than isentropic, so we will consider as WA divided by WS. Okay, when we talk about the work output for the case of turbine, if you remember in chapter number 5, we discussed the first law of thermodynamic application over turbines. Okay, so in that case, since the turbines are considered to be steady flow, steady state devices, so the right hand side of the equation becomes 0. Delta U plus delta kinetic energy plus delta potential energy all goes to 0 because it is SFSS device, steady flow, steady state device. Okay, then we say that on the left hand side of the equation we have Q minus W. Work output will always be there. Q, we said that if it is adiabatic, it is not there. If it is not adiabatic, Q could be there. But in this case, let's talk about the adiabatic turbine. For an adiabatic turbine, Q will not be there. So we'll have the work, and then we have the energy going in and out, difference of the energy going in and out for the fluid going in and out of the device. Okay, so the energy is in the form of enthalpy plus kinetic energy due to the velocity and the potential energy. So for most of the cases, in case of the turbine, the pipe diameter, inlet and exit are the same, so there are no changes in the velocity of the fluid going in and out of the turbine, so the kinetic energy factor will be zero, and also the potential energy effects are zero. The only difference is the change in the enthalpy. So the work will be equals to the change in the enthalpy for the case of the turbine. So here we will have a situation like, for the case of turbine, the work is m dot enthalpy H1 minus H2. This will be the work output for the case of the turbine. Okay, now here when we say H2, so H2 is the enthalpy at the exit. Now enthalpy at the exit depends. Now if we draw the HS diagram, for the case of a turbine, so if for the isentropic process, the HS diagram would be represented by a vertical line because the entropy is constant, because there are no irreversibilities. But for the actual process, the and the for the actual process, the process inside the turbine would not be represented by a vertical line, but by a case where the entropy is actually increasing. Okay, so it will not be represented as 1 to 2s, it will be represented as 1 to 2a. In any case, 1 to 2a will be less than 1 to 2s, because in case of the actual, we'll have more loss of the energy, and so the work output would be less, and in case of the ideal, we'll have no loss, so the work output will be more. So here, when we if we write the formulas for the work, actual work over the isentropic work, it will be m dot h1 minus h2a divided by m dot h1 minus h2s. M dot can cancel because they are the same, so this becomes our formula for the isentropic efficiency of the turbine. So the isentropic efficiency of the turbine is defined as change in enthalpies for the actual case divided by change in enthalpy for the ideal case. And the actual case will always be smaller than the ideal case, so efficiency will always be less than 1. So this is how we define the isentropic efficiency for the case of a turbine. First of all, do you understand the concept here for the isentropic efficiency of turbine or not? Is there anything you want to ask? Please ask. Everything is clear so far?
Yes, it's clear.
Okay. Okay, so let's have a numerical associated with it. So we have a steam that enters an adiabatic turbine. First of all, this is steam, and it is an adiabatic turbine, so the process is isentropic. Steadily at 3 megapascal and 400 degrees centigrade. So this is the P1, and this is T1, and leaves at 50 kilopascal and 100 degrees centigrade. So this 50 kilopascal will be P2, and 100 degrees centigrade will be T2. If the power output of the turbine is 2 megawatt, so that's the power output of the turbine. So work out. Determine the isentropic efficiency of the turbine. First thing is that we need to determine what is the isentropic efficiency of the turbine, and the mass flow rate of the steam flowing through the turbine. And the next thing that needs to determine is the mass flow rate from the turbine. So we have a turbine here, steam turbine. So these are the inputs, P1 and T1. This is the output from the turbine, P2 and T2. Always whenever the values are given of the inlet and the exit, these are considered as the actual values, because the pressures and temperatures are normally the measured values, and whenever a measured value is given in the question, it is always considered as an actual value. So this P1 and T1 are the actual inlet values, and P2 and T2 are the actual exit values. And then we have 2 megawatts which are being produced from the turbine. We need to find out what is the isentropic efficiency of the turbine. If we draw it on the TS diagram, so 1 to 2s will be the isentropic process, and 1 to 2, sometimes it is written as 1 to 2a, sometimes it is written as just 1 to 2, but this will be the actual process. So that's the actual process, and this one is the isentropic process. And obviously, in case of the actual process, the entropy is going to increase. In case of the isentropic process, we will assume that the entropy is constant. Okay, so let's have a look at how can we solve the problem. Okay, so first of all, the definition of isentropic efficiency of the turbine is H1 minus H2 A divided by H1 minus H2S. Okay, so H1 H1 is something we can get simply from P1 and T1 because this is a steam. If we go into the thermodynamic tables, from the pressure and temperature, we can determine what is the enthalpy. Okay, so we're going to use P1 and T1 values to get H1. So H1 is done. I'm not going to go into the thermodynamic table right now with you because since we have gone through the process many times, we started from chapter number 3. So I presume that you guys know how to get the values from the table yourself now. So going into the thermodynamic steam table, and then at a specific pressure and temperature, knowing that what is the enthalpy, this is something, a practice that you have already done before. So I'm just assuming that you know how to do it. So we have the pressure and temperature, and based on the pressure and temperature, we can get the initial enthalpy. Okay, and we can also get the initial entropy. Then we have the exit pressure and temperature, P2 and T2. Obviously, as I told you, that these are the actual values. So we'll have P2 and T2, and these are the actual values. So these two values are going to give us H2, but definitely this 2 will be H2A, because since these are the actual values, so we are going to get H2A here. So here this will be the H2A. Now we need to find what is H2S. If we get what is H2S, then we have all the values to determine the isentropic efficiency of the turbine. When we are considering the turbine, so for the case of the turbine, we know that we want to move from high pressure to low pressure. So pressures are always considered the actual value. So for the case of the pressure, it is always considered that P2S is the same as P2A, which is just P2. Okay, so this is always remember. So here, when we need to determine what is H2S, so first of all, we have P2 here, and then we are going to ignore the temperature T2 because this temperature is the actual temperature. We are going to use S2. And since we know that for an isentropic process, S2 will be the same as S1. So sometimes we write here S2S because this is isentropic. So we have S1, which will be the same as S2. So now we know what is S2. So use S2 and P2 value to determine H2. And this H2 will be H2S because we are assuming S1 is equals to S2. So then once we have H2S, now we have all the parameters with us. We just substitute the values into the equation and get what is the isentropic efficiency of the turbine. First of all, this is the blueprint of the solution. Do you understand the blueprint of the solution? Do you understand the procedure, how we solve the problem or not?
Sir, it makes sense. Say it.
Okay. The next thing is the mass flow rate. We need to determine mass flow rate since we know what is the work output of the case of the turbine. So here the work out will be, for the case of turbine, it will be m dot h1 minus h2 Here we have two different H2s. We have H2S and H2A. Remember, whenever we are determining the work in, work out, Q in, Q out, we are never going to use the isentropic value. We are always going to use the actual value. So the work out actual value will be H2A. So we are going to use H2A here. We already know what is H2A. We already know what is H1, and we know what is the workout. Okay. So since we know all these things, we can determine what is the mass flow rate, and this is how we're going to do the second part. So let's see the solution here. So we have P1 and T1. Corresponding to P1 and T1, H1 and S1 is determined. Obviously it will be in the superheated state, that's why table A6 is used. Then now let's just determine the values for state 2A. So we have P2 and T2, and these are considered as the measured values. So obviously these are the actual values. So corresponding to that, we can determine what is H2A. Okay. The next thing is determining the H2S value. Okay. So we have P2S. P2S will be the same as P2A. And then we have S2S, because we know what is S1. So S1 is the same as S2S. So corresponding to that, when we go into the table, we determine that our S value is between SF and SG. So that means it has to be in the saturation state. So we first determine what is the quality, and then use the quality to determine what is the enthalpy. So we're going to get H2S. And now once we have H2A, H1 and H2S, we can determine what is the efficiency of the turbine. The isentropic efficiency of the turbine is 66.7%. That means whatever the pressure was there, 66.7% of the pressure will be converted into work output, and the remaining will be lost as heat from the turbine. So this is how we determine the isentropic efficiency of the turbine. Yes. Anybody want to ask anything?
No, sir.
Okay. The next thing is we need to determine what is the mass flow rate. As I told you, that the work output for the case of the turbine, it will be m dot H1 minus H2A. We already know what is H2A. We already know what is H1, and W out is given in the question. So we can determine what is the mass flow rate. So this is how we solve this problem. Anybody have anything to ask in the solution of the problem? Please ask. Everything is clear so far?
Yes.
Okay, so next thing is the case of isentropic efficiency for the case of the pump or the compressor. It's the same analogy as we have used for the case of the turbine. So the compressor or the pump is exactly opposite to the turbine. So the turbine uses the high pressure and converts the pressure energy into work out. Compressor uses the work in the form of electrical energy and converts it into high pressure. So we have from low pressure to high pressure movement. Okay, so on the HS diagram, it would be represented by a vertical line for an isentropic process, and obviously it will be represented from a tilted line with an increase in entropy for the case of actual process. Likewise, we did for the case of the compressor, for the case of the turbine. If you remember, for the case of the turbine, we defined the efficiency of the turbine as a smaller value over the bigger value. So here we are going to do it like here, like the same way as well. So efficiency of the compressor is smaller value divided by bigger value. Now here, remember, again, we are talking about the work, but these are not the work output now. For the case of the compressors, these are the work input. Now let's have a think. Let's think about it. Suppose I have a compressor, and that compressor is needed to increase the pressure of a fluid from P1 to P2. Okay, if the compressor is uh, isentropic, means there are no irreversibilities in the compressor. So what will happen? whatever the amount of electrical energy I'm going to provide to the compressor, that electrical energy will be converted into high pressure. But suppose if there are losses within the compressor, then whatever electrical energy I'm going to provide, part of that electrical energy will be lost as heat. And so I need to provide actually more electrical energy to actually raise to that pressure, whatever the pressure I want it to be raised. So if there are if there are losses in the system, okay, so the actual work in this case, for the case of the compressor, the actual work input would be larger than isentropic work input, because these are the work inputs. Okay, so if there are losses, then less work input is needed to raise the pressure. If there are if there are no losses, then less work input is needed to raise the pressure. But if there are losses, then we need to provide more work input, because part of the work input will always be lost. So the remaining work will be used to raise the pressure. So if I need to reach a specific pressure, then the actual case will require more work input than the case than the case of the ideal case. This is exactly opposite to the previous time. If you look here, for the case of the turbine, WA was less than WS. But in case of the compressor, WA is actually more than WS. But the main reason is that in case of the turbine, it was W out. And here, in case of the compressor or pump, it is W in. So whenever we have losses, so actual input needed will be much more than the isentropic input needed. So here, when we say isentropic efficiency of the compressor, it will be smaller value over the bigger value. So here the smaller value is Ws, so it will be Ws over Wa. If you look here, this is inverted now. In case of the turbine, it was Wa over Ws. Now, in case of the compressor, it is Ws over Wa. So here, if we write in terms of the enthalpies, it will be H2S minus H1 divided by H2A minus H1. So this is how we define the efficiency of the case of the compressor. If it is a pump, obviously we are not going to use the H2S minus H1, rather we are going to use Vp2 minus P1. This was already discussed in the last lecture, that if it is pump, then we have a different way of determining the work input, and if we have the compressor, we have a different way of determining the work input. So the efficiency of the pump will be represented in this way, and this will be the efficiency of the compressor. Is there anything which is not clear in the theory of isentropic efficiency for the pump, compressor, or turbine? Please ask.
So could you explain how the actual work is larger than the isentropic work?
Once again, did you say what you say?
Could you explain how the actual work is larger than the isentropic work?
Look, for the case of compressor, we need to supply work input, right? And this work input will be used to raise the pressure. Do you understand this thing or not?
Yes.
Okay. Now, if there are losses within the compressor and I need to reach a specific pressure, I need to provide more work input. Am I right? Because there are losses in the compressor.
Yes.
Okay. If there are no losses, then little work input is needed. Because there are no losses, so whatever the work input I'm going to provide will be converted into high pressure. You get it?
हाँ,
So for the case of the compressor, work input will be larger if there are losses in the compressor. Okay, because part of it will be lost. But if there are no losses in the compressor, then the work input will be less. So Ws would be less than Wa. Is it clear?
okay, that makes sense. Say it.
Okay. So anybody else want to ask anything? Anything is not clear? Okay. So let's see a problem here. So air is compressed by an adiabatic compressor. So we have air here. Remember, whenever we have air, means table A17 will be used. It is compressed by an adiabatic compressor from 100 kilopascal. So 100 kilopascal is my pressure P1 at and 12 degrees centigrade, that's T1, to a pressure of 800 kilopascal. So this will be my P2 at a steady state of zero point 0.2 kg per second. So that will be m dot. If the isentropic efficiency of the compressor is 80%, now this time I know what is the isentropic efficiency of the compressor. Determine the exit temperature of the air. We need to determine what is the exit temperature of the air. So that's T2. And the required power input to the compressor and work in. So we have a situation here that we have air going through the compressor. These are the input values, T1, P1. Output we have P2. Okay, the work input is something that we need to determine. How much is the work input? Mass flow rate is given, and we also need to determine what is T2. So this is the case that we have. Now, first of all, it is air, so it will be table A17 will be used. Now here, whenever we have to use table A17, so we need to look at it. If you remember, we discussed this in the last, that we have to always look at what is written in the question. Is it approximate or constant specific heat values or cold air standard assumptions written in the question, or is it the exact or variable specific heat method that we have to use, or nothing is mentioned? So here, if you look in the question, nothing is mentioned. Air is compressed by an adiabatic compressor from this pressure, this temperature to this pressure at this rate. Isentropic efficiency is this much. Determine the exit temperature and the required power input. So nothing is mentioned. Since nothing is mentioned, so we are going to use the exact method. Exact method, and this is an isentropic process. It's written in the question. Okay, so since it is isentropic method, so we're going to use this one. This is what we are going to use in this question. So we are going to use the VR or PR values with us. So the methodology will be what? So we have P1 and T1. Okay, so anyways, here just for the case of table A17, everything is linked with the temperature only. Pressure is not needed. Okay, so we are going to use the T1 value corresponding to T1. Since we know P1 and P2, so we know what is we know what is the pressure ratio. Okay, so we can use this relationship PR1 over PR2 is equals to P1 over P2. Okay, so we're going to use T1 corresponding to T1. We can get what is H1 and we can get what is PR1. Then corresponding to PR1, using this formulation, because we know P1, we know P2, we know PR1, we can get what is PR2. So corresponding to PR1, we are going to get what is PR2. Okay, and then we are going to go back into the table A17, and then corresponding to PR2, we are going to get what is H2, and this H2 will be H2S, because the table is for the isentropic process. When we are using the R values, these are for the isentropic process. So we're going to get H2, and this H2 will be H2S. Now, in order to find what is H2A, okay, we can determine H2A because we know what is the efficiency of the compressor. So efficiency of the compressor, the formula for it is H2S minus H1 divided by H2A minus H1. So come right here, H2S minus H1 divided by H2A minus H1. Okay, so we will know what is H1, we know what is H1. Okay, we know what is H2S, we know what is the efficiency of the compressor, so we can determine what is H2A. Now we're going to use this H2A value, we're going to go back into the table A 17, and corresponding to H2A value, we're going to then determine that what will be T2, and this will be our actual T2. Okay, so this is how we are going to determine what will be the final temperature, and then we can determine what is the required work input. The required work input will be work in equals to m dot H2 minus H1. Obviously, the H2 that we are going to use will be the actual one. So we always use the actual values. So since we know what is H2A, we know what is H1, we know what is m dot, so we can determine what is the work input. Before going towards the actual solution of the problem, first of all, do you understand the blueprint of the solution? Do you understand the methodology that we are going to use to get different values?
Yes, yes, sir.
Okay. So let's see the solution here. So we have temperature, initial temperature given, T1. Corresponding to T1, we're going to get what is H1 and PR1. So if you look here, we're going to go into table A17. So in table A17, we have 285 Kelvin. Corresponding to get that, we're going to get H and the PR1 value. Okay, then once we have the PR1 value, then we're going to use P2, P1, and PR1 to get PR2. So that will be 9.2672. So once we have that, we're going to go back into the table 9.2672. This is the PR2. So this will be here in between. So we need to do the interpolation. And this we're going to do to find out what is H2S. So once we determine what is H2S, in this step, then we're going to substitute the values into the equation for isentropic efficiency of the compressor. Okay, so then we have everything here in it except for H2A. We're going to get H2A. So once we have H2A, we're going to go back into the table 575.03. So 575.03 will be in between these two values, and we're going to get what is the final temperature correspondingly. So we need to do one interpolation here and one interpolation here. So you're going to get what is T2A. And so the next thing is that we need to find what is the work input. So we have H2A, we have H1, and we have m dot. So we're going to get what is the work input for the case of the compressor here. So that's the solution of this problem. If there is anything which is not clear within the solution, please ask. Everything is clear?
Yes, clear. It's clear.
Okay. The next topic is about entropy balance. Entropy balance is a very simple topic. It's basically whenever you have a process, you have an initial entropy, and then you have a final entropy. And if you want to know that how much is the entropy generation, just subtract the two entropies or determine the difference between the entropy of initial and the final entropy, and you're going to get what is the actual amount of entropy generation. There is one problem associated with it within the throttling process. So I want you to go through this problem yourself, go through the topic yourself. It's a simple process, simple topic. The only thing that you need to do is you need to get the entropy generation, and you can get the entropy generation by just getting the entropy difference, the initial condition and the final condition. So with this, our chapter number 7 is finished. You have some practice problems related to chapter number 7. The solution of the practice problems are already provided to you in the Google Classroom. So with this, our chapter number 7 is finished. If there is anything anybody want to ask regarding the concepts introduced in this chapter, or any problems that were used for the problem solution within the chapter, you can ask. Otherwise, let's have a break of about 5 minutes. You can put your attendance in the chat box, and then we are going to start chapter number 9, inshallah, after that. So, anybody have anything to ask in this chapter?
No, sir, it's all good.
Okay. So
No.
let's have a break of 5 minutes, and after that we are going to start chapter number 9, inshallah. Please put your attendance in the chat box.
Hello.
Yes. Anybody want to ask anything?
No. No, sir. It was just that I just arrived from the university right now, so I couldn't attend the class before.
Okay. Anyways, put your attendance, and the half of the class is still left.
Okay, sir. Thank you.
Okay, Assalamu alaikum students, can you hear me?
Yes, sir.
Yes, sir.
Okay, so we are going to start chapter number 9 today now. Okay, and now this chapter number 9 is basically the start of the second part of thermodynamics. The first part was understanding the different kind of laws of thermodynamics. I was understanding the zeroth law, first law, second law, third law we did not study, but it was not important for us. But then this was the first part. We try to understand the different kind of laws of thermodynamics and their applications over different kind of devices in the closed and the open systems. Now, in the second part of thermodynamics, this is what we are going to do. Actually, this is our main aim, main goal of the course of thermodynamics. We wanted to use the waste heat to produce some useful output. So in chapter number 9, we are going to study the heat engines. We introduced the heat engines a little in chapter number 6. So heat engine is basically a device which uses the heat to produce the work output. So we are going to study the heat engines, and basically this is the kind of a heating engine where the working fluid will be air. Since the working fluid will be air, so table A17 will be the fundamental table for us. Table A17 will be the fundamental table for us in this chapter, since air will be considered as a working fluid. There are actually three different kind of cycles which we are going to study in detail. Okay, and these cycles are uh, Otto cycle, then we have the diesel cycle, and the last one we have is the Brayton cycle. So we are going to study these three cycles in detail. Okay, and I'm going to here in this lecture right now today, my focus would be first to summarize things in front of you in a way that you understand how to remember these cycles and what are the differences between these cycles. So first of all, if you don't understand the Otto cycle, diesel cycle, Brayton cycle right now, no problem. Okay, just go through with me. Okay, and go with the flow, and just try to focus over the things which I am focusing right now. Okay, and we're going to discuss about these cycles in detail as the lecture proceeds, and you're going to understand things much better. Right now, this is a summary sheet. I'm going to be dealing with you right now in the summary sheet, and to explain you things in a way that you can actually memorize. Okay, first of all, when we talk about these cycles, so all of these cycles are composed of four basic processes, and these four basic processes, they occur in a specific sequence. So I want you to memorize this, and this is something that will be common to everything, and once you memorize it, it becomes easy for you to actually comprehend any kind of a cycle. Okay, what are these four processes? The first process is compression. So you have a working fluid, and then you do something to compress it. Compress it means you want to raise the pressure. So we have an initial low pressure and you increase the pressure. So this is compression. And so this is the first process that always takes place in these kind of cycles, whether any cycle, Otto cycle, diesel cycle, Brayton cycle, or any other cycle. So first process will be the compression. The next process will be heat addition. So whatever the process it is, once you have a working fluid, you compress the working fluid. Now you have a high pressured working fluid, then you add heat into it. Now, what is the methodology of heating at? Most of the time, it's the same methodology. Let's say if the working fluid is air, you mix it with the fuel, and then you ignite the fuel, and so an explosion occurs, combustion occurs, and heat is added to the air. Heat is added to the working fluid. So this is most of the time the process. This is how it works. So heat addition takes place. Okay. So this is the second step. This is the second process, heat addition. Then we have third thing, opposite of compression, expansion. So opposite of compression is expansion. So what happened is that you have working fluid now, it's pressurized and heat is added to it. Now you expand it. When you expand it, so you release the pressure, you decrease the pressure from high pressure back to the low pressure. So now the pressure is decreased. This is the third step, expansion. And then the final or the fourth step is the opposite of heat addition, which is heat rejection. So we reject heat. And once we are done with this thing, so we have actually returned back to the first state, to the initial state. And then the process continues like this: first compression, then heat addition, then expansion, then heat rejection. And then
So
it
this
goes, yes.
so this happens in this specific order.
This happens in this specific order. And
Okay.
this happen in all the cycles. Okay, right now my objective is, I'm not explaining you what is Otto cycle, I'm not explaining you what is diesel, I'm not explaining you what is the Brayton cycle, but these three cycles are going to be used, and I'm trying to figure out a way that you figure out a way that you memorize it very easily, very quickly. Okay, so first thing is that, okay, these are the four processes that occurs in all the cycles, and this is the sequence. There's always compression, then heat addition, then expansion, then heat rejection. Understandable?
Yes.
Okay. Now let's try to understand another thing. The other thing is that, look, we discussed about it. There are two forms of energy transfer. The first form of energy transfer is work. And when we talk about work, so work is represented as PdV. And we discussed this in the beginning of the chapter of entropy, where P is basically what it is, the potential for this energy to transfer, and the effect is the change in the volume. And when we multiply the potential with the effect, that's the actual amount of work done. Okay, and if you want to represent it in the form of a graph, in the graphical format, we represent it as pressure in the y-axis and the volume in the x-axis, and whatever the graph it is, the area under the curve will be the work done. So here we have PV graph, very important, and the PV graph is a direct representation of the work done. The next thing is that we have another form of graph, because we know that we have another form of heat transfer, and that is Q, amount of heat transfer. Okay, and that the Q, heat transfer, is another form of energy transfer, and Q is basically TdS, where T is the temperature, which is basically the potential for the heat to transfer, and then the other thermodynamic property is the change in the entropy, ds. Okay, and if we have to represent it in the form of a graph, like we have the PV graph is a direct representation of the work done, then we also need to have another graph for it, and that should be TS graph, where temperature is on the y-axis and entropy on the x-axis. And whatever the graph we have, the area under the curve is a direct representation of the amount of heat transfer. So we have two graphs, very important for all kind of cycles: PV graph and TS graph. And while we know that PV graph is a direct representation of the work done and TS graph is a direct representation of the amount of heat transfer, we also know that the work done and heat transfer are quite interrelated. If you remember in chapter number 6, when we discussed about the heat engine, so our work out was basically what? Our work out was Q in minus Q out. So Q's and W are actually interlinked with each other. Similarly, in case of the refrigeration cycle in chapter number 6, when we studied, so our work in was basically what? It was Q in, again it was QH minus QC, or Q in minus Q out. So it's again the same thing. So the Q's and W's are interlinked with each other, but for the PV diagram is an important for the representation of the work. TS diagram is important for the representation of the Q, and we need these diagrams all together. Anyways, so far everything is clear or not?
Yes, it's clear.
Okay, so let's see Otto cycle. We need two diagrams. Okay, PV, the other one TS. Okay, let's move down. Diesel cycle, we need two diagrams. PV, TS. Let's move further down. Brayton cycle, we need two diagrams. PV, TS. Okay, so we have Otto cycle, diesel cycle, Brayton cycle. These are the three cycles that we are going to study in this chapter. Okay, now it's very simple. What's the difference between these cycles? Very simple. For Otto cycle, we have two vertical lines on the PV diagram. 1, 2. In the diesel cycle, what we do is that the top vertical line, we convert it into horizontal. Bottom vertical line remains vertical. So that's the diesel cycle. In Brayton cycle, now the bottom vertical line, we also convert it into horizontal. So now instead of having vertical lines, we have two horizontal lines. So that was the Otto cycle, two vertical line, then one horizontal, one vertical line diesel cycle, then two horizontal lines Brayton cycle. Okay, again, you don't know right now what is Otto, what is diesel, what is Brayton cycle, but that's not my concern right now. We will discuss it in later. Right now, I'm just trying to figure out a way so that you understand, you memorize things quickly. Okay, so this is how the Otto cycle, diesel cycle, and Brayton cycle looks like. Okay, the next thing that I need to do is I need to connect the lines. Okay, so okay, so this is connected together. Okay, similarly here, sorry, okay. I connect together here also. So I need to connect together. So I've connected them together. Okay, there I missed the connection. Okay, let me take the eraser. Anyways, the connections are not done very nicely because I'm drawing it on computer, so the drawing gets very bad. But anyways, we have the actual drawings here as well, so you're gonna look at it. Okay, now always it is the process goes in the clockwise direction. Okay, so the process goes in the clockwise direction. It's always like this. Okay, so this will be 1, this will be 2, this will be 3, this will be 4. So here it will be 1, 2, 3, 4. Here also it will be 1, 2, 3, 4. Okay. So when I say that we have compression, so compression is always a state point 1 to 2. Heat addition is state point 2 to 3. Expansion is from 3 to 4. Heat rejection is from 4 to 1. Okay, so we always have compression. Okay, whenever we have compression and expansion, they are considered to be isentropic process. Okay, whenever we're talking about the ideal cycles, so they're considered to be isentropic process. So whenever it is an isentropic process, the entropy is constant. Okay, so we have S constant here, we have S constant here, because 1 to 2 is compression, 3 to 4 is expansion. So S is constant here, S is constant here. Again, 1 to 2.
So could you repeat what you said about
Could I
entropy being constant?
look, 1 to 2 is compression, right?
Yes.
So whenever we say the compression is done, we say in the compressor or whatever the device, we assume that the entropy is constant. Okay, isentropic
Okay.
process. Okay, so 1 to 2 entropy is constant, 3 to 4 entropy is constant, because 3 to 4 is expansion. So for
Okay.
compression and expansion, we always assume entropy is constant. Okay, so this is constant here. Again, in the diesel cycle, 1 to 2 entropy is constant, 3 to 4 entropy is constant. In Brayton cycle, 1 to 2 entropy is constant, 3 to 4 entropy is constant. Okay, the next thing is it's very clear if you look on the PV diagram. 2 to 3 it's a vertical line, and 4 to 1 is also vertical line. So vertical line in the PV diagram means volume constant. So this volume constant. In diesel cycle, whenever we have horizontal line is pressure constant. So it's pressure constant here, volume constant here. And in Brayton cycle, we have 2 to 3 is also a horizontal line, 1 to 4 is also horizontal line. So we have pressure constant. Okay. So if I want to write the processes in any cycle, so let's talk about the processes in Otto cycle. So we have isentropic compression, then we have constant volume heat addition, then we have isentropic expansion, then we have constant volume heat rejection. Make sense? This will be the Otto cycle. Then the diesel cycle, constant isentropic compression, constant pressure heat addition, then isentropic expansion, constant volume heat rejection. Then the Brayton cycle, isentropic compression, constant pressure heat addition, then isentropic expansion, then constant pressure heat rejection. So far everything is clear or not?
Yes.
If you look here in the 3 cycles, the only difference is in the heat addition and heat rejection process. Okay, so in the Otto cycle, both heat addition and heat rejection are constant volume. In the diesel, heat addition is constant pressure, heat rejection is constant volume. And in Brayton, both heat rejection and heat addition are constant pressure. Okay, so I have explained you how to draw the PV cycle. Now from the PV cycle, we can also determine how we can draw the TS cycle. So TS cycle have uh, entropy in the x-axis. Now in all the cycles, we have 2 isentropic processes. Whenever we have an isentropic process, it will represent as a vertical line on the TS diagram. Okay, so we'll have 2 vertical lines here, 2 vertical lines here, and 2 vertical lines in this one. Okay, so next thing is we can join them together. we can name them 1, 2, 3, 4. Okay, again we can join them together and name them 1, 2, 3, 4. Then for the Brayton cycle, join them together, name them 1, 2, 3, 4. So practically for the case of the TS diagram, whether it is auto, diesel or Brayton cycle, they all look like the same. Okay, so we have 1, 2 isentropic, 3, 4 isentropic, and here we have constant volume, constant volume. So here 1, 2 isentropic, 3, 4 isentropic. Here we have constant pressure, constant volume. Here we have 1, 2 isentropic, 3, 4 isentropic. Here we have constant pressure, constant pressure. So what I have done with in front of you right now is that I have shown you how to draw the PV diagram and TS diagram for the three different cycles: Otto cycle, diesel cycle, Brayton cycle. And you can actually see what is the difference between them and what are the different kind of processes that are occurring and what is the sequence of them. Okay, and these are actually drawn here as well. If you look here, this is the Otto cycle. Okay, this is the PV diagram. Compare this PV diagram with the one I have drawn. Okay, so it's similar. Okay, then see the TS diagram. Compare the TS diagram here, actual, with the one I have drawn. Similar. Volume constant, it's written here, volume constant. And this is isentropic, this is isentropic. Okay. Then look at the diesel cycle. This is the diesel cycle I have drawn. And look at the diesel cycle here, PV diagram. Then this is the TS diagram I have drawn for the diesel cycle. This is the TS diagram here. Okay, none of the line is horizontal. Even the top line from 2 to 3, it looks like horizontal, but it is not horizontal, because horizontal means the temperature will be constant. Temperature is not constant, so pressure is constant. Okay. So look here in the Brayton cycle. This is how I have drawn the Brayton cycle. This is the Brayton cycle here. Okay, and the TS diagram of the Brayton cycle and the one which I have drawn here. I have not explained you what is Otto cycle, what is diesel cycle, what is Brayton cycle. These are the things I'm going to explain you later. But right now, I have just devised a methodology where you can understand the processes in the cycle, their sequence, and what are the differences between these three cycles. And these three are the main cycles which we are going to cover in chapter number 9. If you understand this thing and this thing stick to your mind, if you remember it, then it will become very easy for you to go through with the rest of the chapter. Okay, so we are going to study all these cycles in detail, but right now my objective was not to explain you these cycles, but to show you a methodology to memorize the steps within the cycles. Everything is clear so far or not?
Yes, sir, it's very clear.
Okay. Okay, so let's keep ourselves till this point here. There are other cycles also mentioned here in this chapter. We are going to discuss about them, but we are not going to study this jet propulsion cycle. It's very similar to the Brayton cycle, but when we are going to come to that, we are going to understand that. Right now, I have explained you these things, this part only. Okay, so this part is something that if you understand it well, that's good. The schematic diagrams, I have not explained you that, but we are going to discuss it later. Okay. So let's so let's start with our lecture for gas power cycles. We call it gas power cycles because air is used. And what's the major difference between the gas and the vapor? We say that vapor is something which changes phase. So sometime it is in the liquid format, then we can convert it into the gas form, then from the gas could be converted back into the liquid. So whenever something is changing phase, we call it vapor, and whenever something is not changing phase, we call it gas. So here we say gas power cycle because we are using air as a working fluid, and the air is going to remain in the gaseous format and it's not going to convert into liquid during any part of the cycle. So this is a gas power cycle. We say it's power cycles because these are the heat engines, and our main objective is to produce the useful work output in the form of power. Now we're going to use this power for what purpose? That's another thing. Sometimes we're going to use this power as just the mechanical output to produce for transportation purposes. So like for example, we have the engines of our car, motorbikes, uh, we have the jet engines of the airplane, and their objective is not to produce electricity but to produce the transportation, to produce power that could be used to transport people. Okay, and then we have sometimes we have engines which are producing power, and the main objective of that is not to transport but rather to produce the electricity. So that's another objective. But anyways, whatever the power or whatever be the form of the power, that's another thing. But our main objective is to produce the work output using gas or means air as a working fluid. So that's the gas power cycle. So this is chapter number 9 we are going to cover, inshallah. These are the objectives of the chapter. Power generation is our main topic here. Refrigeration we are going to cover in chapter number 11. So most of the time what we do is that we are going to consider the ideal cycles. The ideal cycles are the one where we do not have irreversibilities. The main thing is that ideal cycle is easy to analyze, and it gives us the basis to assess the performance of the actual cycles. The real cycles have some complicating effects such as the friction and insufficient time to reach equilibrium. These are some of the irreversibilities within the real cycles, but we are not going to consider the real cycles a lot. We are going to focus ourselves over the ideal cycles within the course. Since in this chapter we will be covering the heat engines, so we already discussed in chapter number 6 regarding the heat engines that the thermal efficiency of the heat engine is work net over Qn. This is the actual thermal efficiency. We are going to introduce some idealizations within it, that there is no friction, no pressure drop, all expression and compression are quasi-equilibrium, the heat transfer from pipes are negligible, and there are no changes in the kinetic and potential energy within the system. So we're going to consider these idealizations in order to make our real power cycles into the ideal power cycles. Carnot cycle is the very first cycle. Obviously, this is the basis to determine the efficiency of any other cycle. We discussed the Carnot cycle in a bit more detail in chapter number 6, so I'm not going to go into those details again. Anyways, this is the PV diagram. This is the TS diagram for the Carnot cycle. This is the schematic diagram. So schematic diagram of the Carnot cycle is here. These are all the processes that occur through them in the right sequence. So just go through them. We already went through them in chapter number 6, so I'm not going to go through them again here, but anyways, it is here. The Carnot cycle efficiency, it's the only thing that we need to do is convert Q's into temperatures, and this should be the absolute temperatures. So then whatever the efficiency we're going to get from here will be the Carnot efficiency, and that is the maximum possible efficiency. That's the efficiency of an ideal cycle. Okay, let's talk about the air standard assumptions. We're going to consider working fluid, air as a working fluid, and we're going to assume it behave as an ideal gas, and it will behave as an ideal gas in reality. Why? Because the non-idealized behavior comes when air is in a stage of when it is close to be liquefied. But for it to be close to liquefied needs very high pressure and very low temperature, and most of the times these cycles are operated at a very high temperature, so they are far away from the state where they can be where the air can be liquefied. So air would behave as an ideal gas. All processes are considered internally reversible. The combustion and exhaust are replaced by heat addition from and heat rejection to an external source. So in reality, when we say heat addition to air, how it works, it's basically a complicated process where the fuel and air are mixed together. The fuel is atomized, they're mixed together perfectly, and then after that it is ignited to combust, and then because of the combustion, the heat is now then added to the air. So these are there are a lot of processes that occur inside this combustion chamber, but we are just going to simplify all of this together in the form that air is going in and then heat is added to the air and then air is going out. So we are just simplifying this here in this chapter, because we don't need to go into the combustion details at all. We just need to know that there is some amount of heat added to the air, which is a working fluid. Again, we have cold air standard assumptions. It's very important in this chapter. Very significant that if it is mentioned in the question that use cold air standard assumption, or use the approximate method, or use the constant specific heat values, then there is a specific methodology that you have to adopt. We discussed that in chapter number 7. And if it is mentioned in the question that use the exact approach, or it is mentioned in the question that use the variable specific heats, or let's say that nothing is mentioned in the question, then you will have to use the exact approach, and that exact approach was also mentioned in chapter number 7. How do we have to use that? So these are the two different solution procedures that we have to follow, and you will see also there in the practice problems, you will have in practice problem the same problem. First you have to solve it by using the constant specific heat values, and then you have to solve it by using the variable specific heat values. And the two procedures are entirely different, and their answers would definitely be different a lot. So these are the things that you need to focus on in this chapter. Okay, now first is the first kind of engines that we are going to study are the reciprocating engines. Most of the time the reciprocating engines are the engines where we have a cylinder and a piston. And so let's first discuss some terminologies associated with the piston cylinder device. So whenever we have a piston and a cylinder together, okay, so the diameter of the piston and the diameter of the cylinder, they're approximately same, and they're given a specific name known as bore. So bore is basically the diameter of cylinder, which is also the diameter of the piston. Then whenever you have a piston cylinder device, so within the piston, within the cylinder, the piston has a topmost position and the bottommost position. The topmost position till which the piston can reach is known as the top dead center, and the bottommost position is known as the bottom dead center. And the piston actually moves between the top dead center and the bottom dead center. When the piston inside this cylinder, inside the region, we have the working fluid. So when the piston is at the top dead center, then the working fluid is totally compressed. So the working fluid is then compressed to this region only. And when the piston is at the bottom dead center, so that is the maximum possible volume inside the cylinder. So we have the top dead center, the bottom dead center. Stroke is basically the length the piston covers while moving between top dead center and the bottom dead center. So this is a stroke. It is basically the length. We have the intake and exhaust valves. Obviously, when the intake valve will be open, then the fresh air is going to enter into the cylinder. When the exhaust valve is going to open, then whatever the gases there inside the cylinder is going to go out as exhaust. So these are some of the terminologies inside the reciprocating engine, specifically the piston cylinder engine. Let's talk about different kind of volumes. When the piston is at the top dead center, so that's the minimum volume. That means whatever the working fluid we have, it's totally compressed, and so this volume is known as the clearance volume. And when the piston moves between the top dead center and the bottom dead center, or it moves from the bottom dead center to the top dead center, so the volume which is displaced by the piston, this volume is known as the displacement volume. The total volume of the cylinder will be basically what? It will be displacement volume plus clearance volume. So when the piston is at the bottom dead center, the total volume of the cylinder will be the displacement plus the clearance volume. Then we have another terminology here, compression ratio. It is represented by R. R is the compression ratio, and it is the maximum volume by the minimum volume. The maximum volume is when the piston is at the bottom dead center, and the minimum volume is when the piston is at the top dead center. And the ratio of these two is basically the compression ratio. And this compression ratio will definitely be greater than 1 all the time. Anybody have anything to ask so far? Everything is clear or not?
No, sir.
Okay. Okay, then we have the mean effective pressure. Mean effective pressure is basically what, since within our piston cylinder device we have the pressure variation from low pressure to the high pressure throughout the cycle. Okay, but anyways, if we presume that the cycle behaves at a constant pressure, that hypothetical constant pressure would be known as the mean effective pressure, and it is basically a fundamental parameter to compare the performances of reciprocating engines. Now, what is the significance of it? There's a lot is mentioned within the book as well, and I want you to search it and go through it yourself. That what is the significance of mean effective pressure? This is kind of your your self-study task. Okay. Anyways, from the formula wise, the mean effective pressure is given by the formula work net divided by the maximum volume minus minimum volume. Okay, and this will be the formula for the mean effective pressure. Now let's discuss about two different classifications of reciprocating engines. The reciprocating engines are the ones which uses the piston cylinder device, and there are two main or fundamental classifications of reciprocating engines. The first one is known as the spark ignition engine. Now the spark ignition engine or the SI engine is a kind of an engine where what happens is that once we add the fuel with the air, we compress the air fuel mixture, and then for the combustion to occur, we need to have a spark plug. The spark plug is a device which produces the spark, and this spark is enough to combust the air fuel mixture and do the combustion. So since the combustion for these kind of engines occur because of the spark produced by the spark plug, that's why these kind of engines are known as spark ignition engines. The ideal cycle for the SI engine is known as the Otto cycle. The Otto cycle which we just discussed before. And these are basically the petrol cycles, the ones which are normally used in our motorbikes, in our cars. They are basically the Otto cycles. They are basically the petrol cycles. They need the spark plug to do the ignition. Okay, so these kind of cycles are known as SI engines, and the ideal cycle for it is known as the Otto cycle. Otto was the scientist who generated this cycle, so that's why it's named against him, which is the Otto cycle. Normally, Otto cycle uses petrol. Okay, so this is the spark ignition engine. The second engine is the compression ignition engine. In case of the compression ignition engine, it is different from the spark ignition engine in effect that when you mix the fuel with the air, the compression is done to the stage that the pressure and temperature rise so much that the air fuel mixture ignites on its own. Combustion occurs on its own, and you do not need a spark plug. So if you mix the air and fuel and you compress it to such an extent that the pressure and temperature rise of the mixture to that extent that automatic ignition occurs, automatic combustion occurs, then this kind of engine is known as a is known as compression ignition engine. The ideal cycle for this kind of an engine is the diesel cycle, and the diesel cycle is known as diesel cycle because the scientist who discovered this kind of cycle was known as Diesel. His name was Diesel. and it uses a specific fuel, and you know the fuel, which is diesel. Diesel is a specific fuel. It's comparatively very thick fluid compared to petrol. Okay, and diesels are normally used in heavy machinery. Okay, so these this kind of fluid is used in the diesel engine, where we don't have any spark plug, and the ignition is done by auto ignition by reaching a specific temperature due to compression, where the ignition happens on its own. So this is known as diesel cycle. Normally these diesels are used in the diesel cycle, and diesel cycle is used is basically in the trucks, heavy trucks or heavy machinery. So this is the basic difference between spark ignition and the compression ignition engine. Diesel cycle is also something that we already studied before. There is only one small difference in thermodynamically within the cycle, that the heat addition process in case of the Otto cycle is a constant volume process. In case of the diesel cycle, it's a constant pressure process. Otherwise, the rest of the things are same in the Otto cycle as well as in the diesel cycle. But anyways, do you understand the difference between Otto cycle and diesel cycle, or the spark ignition engine and the compression ignition engine? If anything is not clear to anybody, please ask.
No, sir, that would be all.
Okay. Now, next thing is we are going to start with the analysis of the Otto cycle, but at this point, I'm going to stop here today. And inshallah, in our next class, we are going to start with the Otto cycle. Next class, inshallah, we're going to cover the Otto cycle and the diesel cycle both. And then in the next class, inshallah, we are going to finish chapter number 9. So this is going to be a big chapter. But anyways, I'm going to stop here at this point. Anybody have anything to ask so far within the chapter? Anything, any concept not clear? So please, you're more than welcome. Please feel free to ask.
It's all good, sir. Thank you.
Okay. So if it's all good, then you can leave the class if you want. Our lecture is finished.
Okay, sir. That's
Right.
So thank you, sir. Have a great day. Allah Hafiz.
Thank you. Same to you.